Good afternoon, Professor. How are you?
Fine, thanks.
The first thing I wanted to discuss with you is that you were jointly awarded the 1973 Nobel Prize in Physics for predictions of the properties of a supercurrent through a tunnel barrier. And so the Josephson Effect involves a supercurrent flowing indefinitely long without any bias applied across a Josephson junction, which is made of two or more superconductors coupled by a weak line. Can you outline more or less what's a Josephson junction and what's the Josephson effect?
I got very interested in superconductivity when I was a research student. I was about the only person who could understand the theory in that group, so I got into it trying to understand what superconductivity really was. The thing that seemed most relevant was that there's a kind of wave. That wave, the interesting thing was that wave had a phase, and I wondered, did that phase have a meaning? And I thought about this and came to the conclusion that if you had two superconductors, each with its own wave, the phase difference could be something meaningful, but only if you could couple the two superconductors together. So I then was able to work out what current you would get if there were two superconductors joined by a weak link, and that was the effect basically. It's that current was sensitive to the phase. And it had various consequences like the quantum interference, for example, and the way frequency and voltage difference were connected. So that was it, basically.
What sort of environment was there when you discovered these concepts? I mean, at the Cavendish Lab, what sort of environment did you have around?
Some people were skeptical, but Professor Phil Anderson was visiting, and he'd actually worked on this idea of a phase in a superconductor, so he was very positive about it. So everything was okay then, but of course I was working on conventional physics at that time, so I didn't encounter any difficulties.
So basically you were the seventh youngest person who got a Nobel Prize in physics. You were 33 when you got the award. Did that change your plans?
Yes, one thing was I had an enormous number of contacts. I thought the next 6 months I'll be spending answering letters, but it went on much longer than that. That's one side. It did on the other hand help in that people felt they couldn't stop me doing ideas that they weren't interested in. So I got invited to lots of conferences and so on. But
basically the mindset in academia and in general, and also at the Cavendish Lab in particular, have changed quite a lot during the past decades. And now there is a lot of push towards scientists so that they can get involved into startups and entrepreneurship and so on. I mean, I guess when you did these discoveries, there wasn't such a thing, or maybe there was, I don't know. Did you get any push towards writing patents and spinning off these ideas into a company?
No, actually, my supervisor, Brian Pippard, was against the idea of patents, and he was against the idea of turning everything you wrote into to produce lots of papers. But that certainly changed. People encouraged to do lots of papers and so on, and it's not been very good. And they have to spend a lot of time applying for grants. I've been less involved with that because I don't seem to be able to get grants anyway, so I don't spend much time applying for funds. Fortunately, as a theoretician, I don't need much in the way of funds.
And what sort of devices were built with your discoveries?
Yes, well, one of the main ones was the superconducting quantum interference detector, or SQUID. That involved two of these junctions in parallel, so it was like a double-slit experiment. It measured the phase difference, and it turns out that the phases are governed by magnetic fields. So it was in fact a very sensitive magnetic field detector. Apparently the Australian government has made quite a bit of money from it because they've been able to prospect for materials using these magnetometers. It proved to be a way of measuring voltages very accurately, so it's had application in terms of measuring fundamental constants And the other thing is infrared detectors. Apparently, people are able to use them for detecting weak infrared signals.
After your Nobel Prize, there were another 8 Nobel Prizes awarded to scientists working at the Cavendish Lab. And before that, there had been 20 Nobel Prizes between 1904 and 1973. But after 1982, there has been a long period of silence of 37 years until the award of a Nobel Prize to Didier Queloz last year. And do you think this kind of silence is due to the sort of direction of the Cavendish Lab or to something else? What do you think?
I'm not sure. I mean, there's, I suppose, an element of chance. I don't know, was Didier Queloz at the Cavendish, or he was in astronomy, wasn't he?
Yeah, astronomy, but he did his research at the in Geneva, I guess. I mean, when he did the discovery, it was 1995. He did that in France. He wasn't with the Cavendish. He joined the Cavendish afterwards. Yeah.
Well, I can't say, but I suppose there's a cumulative effect. If you have enough very good people, that attracts more people. And yes, I don't know if maybe it hasn't got the reputation it had in the past. Mott and Hewish and so on were around then.
So you told me how you got interested in TM, and how was that influential for your subsequent research activities after the 70s? Did that have any impact in your research?
Yes, well, I was interested in sort of consciousness, deeper states. So it did influence my research. Well, one thing I felt more in connection with the psychic phenomena, which we might get onto separately, but that led me to feel that regular physics wasn't really taking into account the mind enough. Eventually, I decided I'd form what I call the Mind-Matter Unification Project, discussing how mind and matter fitted together.
So in this talk that I mentioned before, you spoke about intelligence. About a week ago, I did a podcast with a very famous researcher on intelligence and IQ. It's called James Flynn. And it describes intelligence as, by intelligence, it means that you can do tasks that are required by your environment quicker and better than the next person. But I guess your definition of intelligence is different. So what do you mean by intelligence?
Well, it is actually very much like solving tasks. Processes, well, it's like in artificial intelligence. Achieving a goal requires very specific methods, and that's how I see intelligence. And mind partly uses intelligence. But the intelligence is more of a creative aspect, and once your creativity has enabled you to solve a problem, you can then apply those solutions to other problems.
Was the talk an attempt to bring physics into TM or TM into physics or something else?
More the concepts behind TM, which come from the Vedas. So I'm collaborating with people who have studied that in detail. And so what I find is that conventional physicists sort of start from physics and try and put in mind, physics and biology, whereas with the Vedas you start from the structure of mind, starting from the opposite end, so really you need to work with both.
So it was an attempt to find some sort of suggestions from these texts, so that you might get the ideas for physics, basically.
Yes. Well, the point is there are various levels of mind, and ordinarily we only study ordinary mind, but with meditation and so on, you get into contact with the deeper aspects of mind, and that might tell you really where it all comes from.
You spoke about science orthodoxy, and I mean, we know that Nobel Prizes are awarded for breakthrough discoveries, and often they involve going against the orthodoxy. I mean, and also before Nobel Prizes, we can think about, well, Einstein got a Nobel Prize, but he went against the orthodoxy, especially with the theory of relativity and so on. But before that, Galileo, for example, he went against the orthodoxy. So how would you define scientific orthodoxy and consensus and acceptance? And when do you think orthodoxy is necessary? And when is it a bad thing?
Well, first of all, I would say that Nobel Prize isn't necessarily anything unorthodox. It may just be a perfectly orthodox new discovery.
Yeah. In some cases, yes.
I view the scientific community as a bit like a club, and that seems it has its rules and you mustn't break the rules. For example, you mustn't in any way express support for intelligent design or you might be out of a job. Memory of water is a bit similar. You must dismiss homeopathy. The paranormal is a bit different because it turns out that
The paranormal.
paranormal, yes, quite a number of scientists do believe there's something to the paranormal, telepathy and so on, but they have to keep quiet about opinions or it might be counted against them. So you don't hear very much of orthodox scientists.
But if I'm not wrong, the American government was researching on paranormal activities, I guess.
The American government was researching on, or Department of Defense was researching on something called remote viewing. This was actually used. The people who were hostage in was it the Iranian embassy, and they actually used it to find out information about them. And in fact, President Carter apparently mentioned this once.
So what do you think is the role of media in consolidating or discrediting scientific research? Because the media has a huge power, right? Sometimes they might discredit, other times they might boost certain scientific discoveries.
They may often concentrate on the spectacular. I would say they tend to be orthodox. Perhaps they don't want to be attacked. So you very rarely find an article supporting things like the paranormal. Well, it's variable. I think they've not been as helpful as they might be.
But I guess, I mean, with media, you can also influence media if you have enough resources. So let's say that there was some billionaire that was supporting paranormal research. Maybe that would have a good treatment by the media.
Could be. I think some of the media, especially, I don't know about cold fusion. I think if it's considered disproved, that's a whole issue that it was considered disproved, but on superficial grounds. I mean, a lot of people try to reproduce the results of Fleischmann and Pons. Some were successful, including Bombay Atomic Research Center, for example. Others failed. The ones who failed didn't appreciate that if you're working with materials, you may get variable results. And so, since they didn't get it to work, they said it's nonsense, and that somehow got to be the accepted fact. Well, the journals are relevant as well. I mean, the journals, I think, have more of an influence in the media. If journals block certain things like telepathy, then the research can't get the publicity that it otherwise would have.
And so that brings to the discussion about the gatekeepers. One of the gatekeepers are publishers, but also archive. And the way I see this economy of science, I would say, is that, I mean, since the introduction of the H index in 2005, there has been a lot of change in academia. And basically now we have a system in which, there was this system before as well, but a system in which universities compete to get the best students, the best talents, the best postdocs, professors, and so on. And so what makes a university attractive is often the ranking. Rankings are based on several parameters and so on. For example, one can look at the Nature Index, and basically scientists compete, and are often evaluated for position based on their H index, on the impact factor of the papers that they publish. And so basically, my opinion is that scientists and universities work more or less like social media. It's a popularity contest. And the other problem with the big journals like Nature or Science is that they set what is a popular topic. So if Nature or Science decide, okay, this is popular, that has a huge impact on the scientific research community because scientists will move to another field. I can tell you briefly, in my case, I was working with the bulk heterojunction solar cells, so plastic electronics, and then perovskite came, right? And then we all moved to perovskites. And why we moved there? Because you have more chances to publish in high impact factor journals, you have more chances to get jobs and so on. So it's a vicious circle from my perspective. So what do you think about this system? Do you think something has to be fixed or it's fine as it is? What do you think?
Well, there certainly is this problem of maybe a vicious circle. positive feedback. String theory is one thing, for example, that is the in field, and so maybe it's easier to get funding for it and so on. Other directions may have more problems getting funding or getting published. Nature may be particularly receptive to ideas that seem popular, but I should say that there are journals like the Journal for Scientific Exploration, which are open-minded. They have careful refereeing, but they won't block a paper just because it's considered wrong. But of course, hardly anybody knows about the Journal of Scientific Exploration. It's particular emphasis on orthodox ideas, I suppose, but maintaining quality.
Yeah, but that's the thing, that maybe someone checks, oh, what's the impact factor of the journal, and then they say, oh, that's low, we want to publish in high impact factor journals because then we can get jobs and so on. So it's crazy. You also spoke about the filters with archive. That sometimes it's even difficult to put preprints in archive.
Yes, I hope with a new director things may improve, but we don't know. But it's been my experience that, well, on the whole, they've accepted the papers, but the problem is there are many sections of the archive, and they typically block my papers from appearing in the sections I feel are most relevant. So, I mean, I feel my ideas are relevant to quantum theory, but they won't let them be published there.
Does it depend on the section for which you have access, or is it a general practice? Because I think I have access to condensed matter, and maybe if you wanna, I don't know what access do you have in there. Maybe it depends on the field.
Yes, that's quite likely to be true. I mean, I talked to an experimenter and he said people never had any problem. The one thing, Ginsparg devised some software which was supposed to decide if a paper was scientific or not.
A software?
A program. Trouble is, it was trained on a certain kind of paper, so any novel paper would tend to get dismissed by the software. Well, then it goes to moderators, and I don't know quite what the moderators are, but they emphasize it's not refereeing. They just therefore look rather quickly and just seem that there's a tendency to block innovative ideas. It should be the means of propagating innovative ideas, but it's rather the reverse.
You can upload archives on ResearchGate now, and they give you a DOI. And doesn't look like they block anything there.
Yeah, so I upload things to ResearchGate, no problem. That is sort of not an official archive, but I also use Phil Papers, which is a philosophy archive. I've never had any problem there, and if my papers have a philosophical side, I upload them there.
When we spoke, I referred to a book called Against the Method. I don't know if you read it, and the author says that there is no such a thing as the scientific method, so all approaches to science should be allowed, including explicitly supernatural ones, and there are no methodological rules which are always used by scientists. And he makes a reference to the story of Galileo that went against Orthodoxy and so on. So do you think science should look at different aspects of knowledge, or even religion and superstition and so on? What do you think? To get ideas, I mean.
No, there's a clear distinction between scientific knowledge and religion. So I don't know if he was saying you should count religious knowledge in there. I mean, spiritual knowledge is okay, but one must. It's clear that it's not done by a scientific method where you test hypotheses by some rigorous method. However, I would emphasize that there's not just observation but theory, and there may be different kinds of theory, and basically, well, I suppose the important thing is it should make predictions, but I think in the early days it may not have to make predictions. It may be a thing that's of interest. That has maybe gone too far with things like string theory, because those theories don't seem to be able to make any testable predictions, but they it's a bandwagon effect, and people find them very interesting. So you can't say that that's the really scientific method. But I think with mind-matter unification, I think we'll gradually get some clearer theories, and these will be connected with experiments more and more. Like you may have a theory which applies well to how people develop and how intelligence works. So, but I don't see this as not science.
No, I think the guy was referring to the fact that when you go to school, they teach you how scientific knowledge is according to Popper, and what the guy is saying is that, well, there are many different approaches. Science is not only done with the rigorous Popper method, but there are many aspects, including environment, culture, even the time you spend in the pub with your friends discussing about things. Maybe you meditate and so on, and you might get ideas from different points. And that's what that guy meant, I guess.
I don't know what point he was trying to make, but I mean, you may get knowledge from talking to friends, but that I think it's important to distinguish that knowledge from scientific knowledge.
Yeah. I think it was referring to intuition, I guess.
Well, again, intuition is a help, but it's not the same as science.
Yeah, that's a starting point, I guess. Just a starting. Then you need to be rigorous and so on, of course. You need to build up a theory, and then you need to do measurements.
But regarding Popper, I mean, it's been pointed out by people like Lakatos and Kuhn that real science is different. You don't, the theory might be disproved, but you may be able to patch it up, and that's part of science. Kuhn is talking about developing from a totally new start and developing a new paradigm. And I think that is perhaps the difficulty. New paradigms may find problems.
Do you think scientific research in academia should be done for the sake of knowing, or done to support certain discoveries that might help building gadgets? Or do you think this building gadgets should be only done by companies? So we have two things: knowledge for knowledge and knowledge for something.
Well, I don't see why it can't be done in universities, and it might help to bring in money into universities.
What sort of funding mechanism would you suggest to finance unorthodox science? Because I guess if you're doing unorthodox science, people might say, "Oh, that's wacky science. You shouldn't be doing that." But maybe you want to do it. So how do you get money for it? Because you need money to build a lab and so on. I mean.
Well, I think official research councils should be open. Of course, there are funders, philanthropists who do fund unorthodox research. And they have their own biases, of course. My research tends to be too unorthodox for conventional sources and too orthodox for unorthodox sources. Perhaps, I don't know.
I saw your talk it was at the Trinity College last November, where you talk about the new scientific paradigm.
Yeah.
And so basically the thing is that there are some areas in which physics seems to be stuck. It's not really progressing. Is it what sort of field are you trying to address? I mean, what sort of aspect do you want to address with this new paradigm?
Well, I don't like the word new paradigm. I think it's just extending physics by realizing that there are some directions it's not looked into, like you might have something new like magnetism introduced by Faraday, was it? And you recognize that there's some limitations in what the physics community addresses. And as I see it, the problem is mind and intelligence. The point is, if you ask about biological systems, the conventional picture is that ordinary physics covers it all. We know what biological systems are composed of, and we know there are things like chemical reactions, and so it's all explained. But in fact, it's not really all explained, because there are points of detail, coordination and things like that, which are important in determining behavior. So for a start, you need to put in coordination, which is one subject that biologists are interested in. Also semiosis, which is about meaning. That's another direction in biology called biosemiosis. My point is there are really two cultures. Some biologists study these significant aspects of biology, but physicists don't know about them. It's not regular physics. The reason why it's important is I think it's important at a fundamental level because the mysteries of quantum mechanics, in fact, could be understood in these terms. People like Karl and Ballard, particularly, who've emphasized parallels and suggested we can understand quantum physics if we take into account things like agency and the way, coordination again. So in other words, we're not understanding the quantum domain properly because our theories don't take mind into account, and therefore we end up with statistical theories. But the theories don't have to be statistical, and I think it'll be a great advance in physics when this is acknowledged and we start to to do theories which take into account things like meaning and coordination, and that's the thing I'm interested in doing.
Yeah, so from one side we have quantum mechanics that does sort of quantitative measurements. On the other side we have biology that does qualitative measurements, and you're trying to get ideas from biology, from biosemiotics, so that you might use this qualitative description into quantum mechanics so that we can understand it, right?
Yes, that's an important point.
Yeah.
Physics tends to insist that you have quantitative theories, but you can perfectly well use modeling to test the theory. The other point is, on the biological side, you have great variability, so your quantitative theory will not apply in general. So you need a different kind of theory. Biologists come up with these different kind of theories. So one needs a kind of synthesis, and I think the quantitative side should come out as some kind of limit when shaping factors lead to precision.
This concept of the fact that we don't understand quantum mechanics is a very old problem. In fact, since the inception of quantum mechanics, there were some physicists that said, well, we don't understand these statistical concepts and so on. And then instead other physicists said, just shut up and calculate. And I think Feynman mentioned this problem. And now, as far as I understood, if you want to investigate the meaning of quantum mechanics, there isn't much funding on that. There is more funding on using quantum mechanics. I mean, we can use quantum mechanics, but we don't understand it.
You left out David Bohm because he's somebody who did combine the two. He worked on physics and on deeper issues, and his collaborator Basil Hiley has worked on details, and I think they've been making progress. So it's not some physicists have been taking that direction, but they're not mainstream. And apparently Oppenheimer led a movement to ignore Bohm.
And I was reading an article by Sean Carroll where it says, it summarizes the thing that we don't understand quantum mechanics in 2 points. He said that, well, of course, the first problem is the measurement problem. That a quantum system does one thing before we measure it, and then another thing after we measure it. And then there is the ontological problem that we don't know if quantum mechanics represents the world as it is, or if we need more. For example, quantum mechanics doesn't involve anything about relativity, and we don't know how to combine quantum mechanics and relativity, so it doesn't provide a complete.
Quantum mechanics does involve relativity. It's putting the general theory, putting that in is wrong. Yes. As you say, there's a problem combining quantum theory and general relativity, but the problem is observation is not properly taken into account, and it's just sort of something that happens. Whereas people like Ballard would say the observation is important, and people like John Wheeler, they talked about subject and object. So you say the subject side is important, and that goes in the direction I'm talking about. And the ontology Well, I think the point there is that reality is too complicated to be able to describe it in mathematical terms, so quantum mechanics is not going to be able to help.
And so coming to the mind-body dualism, and then you say we should unify mind and matter and so on. And so I was looking into this thing, and so this mind-body dualism, I think it comes from Descartes. And then, as opposed to this duality, there are monist theories. You say that we should unify mind and matter, right?
Well, I'm saying that physics should take into account both mind and matter, and it's not doing a good job in mind as well.
So, how would you define mind? What's mind? Is it something that emerges from physics, or is it something separate? Is it like what do you mean by mind?
Well, we already have information, and it's recognised that information seems to be important in quantum mechanics. The question is what is done with information, and that's the sort of physics tends to regard this as a technical matter, but as regards, I think it's fundamental that there are processes involving mind which achieve particular things, and so that's the side of physics which, if you simply observe matter, then that sort of leaves that out. So, in other words, it's your selectivity, the paradigm is saying we do certain experiments, and these experiments only look at certain things. So the paradigm needs to shift a bit, but I think it doesn't have to become, maybe it'll be a new paradigm looking properly into mind.
But in this case, mind refers to what we more or less understand as a human mind, or does it mean that there is mind in objects and things, or?
It's much more general, which is a point that I would emphasize is matter does all sorts of things.
Yeah, so you spoke about biology, and you draw the parallels between biology and quantum mechanics, so different approaches in that table. I think that table was originally in a paper that you wrote in 1988, I think, where you show a table, quantum mechanics and biology.
Yes, that's important, and suggests that...
and then you spoke about the unified approach.
There's a parallel as mind-matter unification in that there's network science, and network science develops its own rules, so it would be a bit like that. But mind has its own special features which may not be in network science. We could call it, as Alex Hankey does, complexity biology.
I think you were referring also to the fact that quantum phenomena don't appear in biological systems, and but then there is some research that has been done in the past 20 years that show that people discovered some quantum effects in biological systems in the field of quantum biology. Have you seen anything about that, especially when it comes to the olfaction or the way the birds orient themselves?
The usual idea had been that quantum effects don't occur at room temperature, but that is not necessarily correct. After all, even the chemical bond is a quantum effect at room temperature. And closely related thing is entanglement, that people are beginning to feel that quantum entanglement is a much more widespread process. It just doesn't just occur in special conditions, and the entanglement remains, and it's a bit of a mystery. That will, I think, connect with mind.
So the other thing that I was interested in is because you mentioned the Winograd language. So this Winograd guy, developed a program called SHRDULU, which is a sort of natural language understanding that was developed in Lisp. So this kind of approach to artificial intelligence called a traditional AI. So basically there were these guys that were thinking they could develop an AI system using logics and semiotics and all these things. But then Dreyfus said that probably this is not the best approach for AI, because I was quoting Heidegger that said that basically human intelligent behavior cannot be formalized. And in fact, this was sort of confirmed with the success of neural networks. In fact, neural networks are very different from standard logical, I would say, Lisp programs. The problem with the neural network is that you don't know what it's doing. You have no idea what it's doing.
Yeah, it's an evolving system, and that again points to the fact that the intelligence and mind might not be treatable in the usual method involving precision. It's more a question of certain principles. I might mention in this context Scott Kelslow's Coordination Dynamics. He has a review paper on this where he compares the usual approach with how coordination dynamics works. And you study this kind of system in a very different way. You look for things which are connected, and you don't presume that it's something very special, very specific in advance. A rather different paradigm as well.
I was trying to understand the circular theory, but I didn't understand it.
Well, Alexei Yardley contacted me, must be over 10 years ago, with ideas, and I think people felt there's some sense to them. It's about units and how they connect with each other and how structures develop. And I think she has an intuitive idea as to how things develop and how, well, she has her own version of coordination. It's the way two systems work together. That seems to be an important concept, and it does seem to be an important process. And also she talks about how, well, we're familiar with the idea that you can sometimes see a system as a unit and sometimes as a pair of things. And again, you have coordination, which makes them act as a unit. And somehow the way two go into one and so on. So it seems to be they're intriguing ideas, I would say, and they've partly assisted the work I'm doing. And in fact, well, we haven't really developed it yet, but I think this idea as to saying something about structure, which may be very important, but it's work in progress.
And another thing that I found very interesting, especially because it looks nice and cool, is the cymatics. Especially if you do music, you find that very interesting. And basically there is a guy called Stuart Reed that developed this device. Well, he's not the first one that discovered this effect. I think it was Faraday the first one that discovered this effect. I mean, would you explain what it is? And
well, simply the effect that if you apply sound to a liquid, usually water, that then structures build up. Faraday apparently discovered this. What John Stuart Reed did was to invent a gadget he called a cymoscope, which enabled you to take pictures of it and treat it very rigorously. You got a vessel where you vibrate the bottom, and then you have a light source reflecting off it, so you can see how it happens. And you can then explore how different kinds of sound have different effects, like it might be music or sound of different frequencies. So that is real rigorous science, you might say, experimentation. He also found something rather interesting, which, well, it was an experiment with dolphins, where dolphins apparently are aware of their surroundings by reflecting sound of objects. So he found that if you took the dolphin's sound and applied that to water, that could also generate a picture. That's a fascinating effect, and may suggest that water can have some kind of intelligence, which gets one into the question of memory of water and so on.
so in this case, what does it mean, intelligence?
Well, water has a complicated structure, and I don't think anyone would disagree with that. Some people would say the structure cannot have a memory because things happen very quickly. That's a fallacious argument because you may get organization which persists. So the idea behind memory of water would be that if you applied a sound signal to water, you could set up particular structures, or you could do it with a biologically active substance. So there's a kind of informational activity, you may say, that's present in water. And as Cavendish suggested, these signals may have biological effects. So in fact, this thing I've been talking about of extending physics by taking signals into account, that may be extremely important in biology. It suggested you can actually treat diseases like cancer by applying appropriate signals. In fact, there's evidence, I think, that cancer cells may be affected selectively by signals. But then water would be a part of this. So as a whole, not very clear what the detail is right now, but almost certainly something there to be discovered.
You also spoke about homeopathy and all these sort of things, but you said that there's a memory effect that they don't last long, or do they? Because I mean, if you're doing a medicine, they're supposed to last longer, right? But if they disappear, then it means that you're just drinking water, or maybe there is a different story. Well, what's...
Yeah, it's a fallacy saying that liquids can hold a memory, because in fact liquid crystals show that. So it could be an organized structure. So it's one of the typical faulty arguments used against memory of water to say that the memory can't persist.
You closed the discussion, the talk you gave last November at the Trinity College, saying that the various concepts fit well together like pieces of a jigsaw. How do they fit together? That's my question. Or it's still being developed?
It's maybe consistent with the second law of thermodynamics. We know when you form a crystal, atoms fit together in a particular way. In the same way, patterns of movement may fit together. Certainly must happen. And so you can say maybe it's a natural development that can occur. What happens when people develop new ideas is that something appears which fits together nicely with what's there altogether. And this is not contradicting the second law of thermodynamics any more than crystallization is. So that's, I gave jigsaws as an example, but it's the idea that things can fit together. An example is a statement and its meaning, or shall we say the description of an activity and the activity itself. Those fit together. While activity is occurring, you describe it, or you work on a description. So these are things that fit together. So this seems to be a key idea, and it's may happen in a very large scale, and this particularly happens with language, I think, and is very complicated with language. There is yet another piece of the whole puzzle.
Probably you don't want to talk about politics, so I'm not going to mention what. But I'm going to ask you, what do you think should be the role of scientists in society? Do you think scientists should influence politics, or they should stay away from politics? What do you think?
Well, I see there's no reason why individual scientists shouldn't influence politics. I think this is sort of happening with the Second Sage Committee. It's scientists who want to collect the evidence and persuade the political scene. I can't see anything wrong with that.
I told you that there is a paper, probably you read it in Nature, where they mentioned this group. I think they had some links with Google, where they tried to reproduce the old 1989 cold fusion experiment, and then, which is this sort of measurements now are called low energy nuclear reactions. And they mentioned that they failed to reproduce it. And then they said, oh, but in the process of all these things, we discovered new measurement methods, and we published many papers and so on. And anyway, so they were talking about call for action, that it's a good idea to keep investigating on cold fusion because it might be promising. I've been following Rossi development with the ECAT since the past 10 years. And I think the problem there is that the guy is also trying to commercialize the device that he claims can generate an excess of heat. But then I was checking before we did this interview, and I found that this group of Australians basically offered Rossi $1 million to get the device and open it up so that they could check whether it's fine or not, and the guy refused. And so what do you think? What's going on with cold fusion now?
Well, they pointed out that it's difficult to do the experiments, and so one shouldn't conclude much, as you said, from the fact that they weren't successful. Yes, well, how is it now? Well, I think I said it got discredited, but research went on in the background. Things didn't work out as well as people hoped, because people hoped that you would just find out how to produce large amounts of energy, but then it turned out it was very difficult. There were methods which were fairly reliable, but they didn't produce a lot of energy. So that's a problem now. However, some people are claiming they're developing methods and patenting them, and sometime in the future they will have this source of energy, but they don't want to talk about it, presumably because they want to be the people who make money from it. So that's what the situation is now. I sure hope that it will come to fruition, and we will be using it to make clean energy, and have to rely less on fossil fuel or the other methods which may take up large amounts of space or something to have your solar energy. Incidentally, I might mention that there's almost certainly a commercial aspect here, and it may be that people involved with conventional energy have assisted a little bit in suppressing the reputation of cold fusion.
So the final thing I wanted to discuss is the PowerPoint you sent me. I think it was prepared by your postdoc. Is that correct? About the Vedic and the quantum. I'm not an expert of this text, but I understood that these Vedas are a large body of religious texts originating in ancient India that were conceived 1,500 years before Christ. And I understood that you are, that I might be wrong, then you correct me. Okay, so this is my interpretation. That you are trying to find scientific elements within the Vedas?
They perhaps have been used in connection with spiritual practices, but they're primarily, as Maharishi pointed out, are a sort of textbook about the nature of consciousness. And in fact, Maharishi would say that they are actually present in consciousness, part of a structure of reality, and they're helping to create it. And studied a little bit of it.
Yeah, so my question is that, because I mean, I've seen this in other monotheistic religions where basically you have people that take new discoveries and then they try to find some hints of these scientific discoveries within the old texts, and just to justify that those ancient texts might have some scientific truth. So my question is whether that's the sort of approach of like providing scientific truth to this text, and then maybe you say, okay, there is science in this text. Let's dig more into this text. Maybe we find more science. Is that the sort of idea? Or?
Yes, I'm not sure about saying, oh, this was predicted by the Vedas. I think, I think to the extent that they are an account of consciousness, it would be useful to use them to guide one's theories. They're actually incredibly complex, so one would have to be selective, but still I think one may find important principles. That may be the first 9 words of the Rig Veda contain it all, in a sense.
So what's the motivation of this work? Does it link to the previous work, or it's a completely new kind of research program? Is it
just one aspect of getting mind integrated in the physics, a useful source of ideas which you won't find in conventional cognitive science.
And I saw that your postdoc mentions the integrated information theory. It says that suggesting that a fly might have some sort of consciousness, like a fly is conscious, or anything can be conscious, right? Even a robot could be conscious one day, who knows, in future. And this integrated information theory is a sort of theory that tries to quantify consciousness. So do you think consciousness can be quantified? Is like formalized, I would say, not
to some degree, perhaps.
I think I saw that in an interview that you were mentioning that you're kind of supporting kind of view of intelligent design. What sort of position do you have? Because there are many positions, right?
Well, I think I don't. You have to be careful about the word, but the way I see it is that the process of building up reality starts from a very basic level, and to some extent, the ordinary universe studied by physics is a product of a certain process of mind. So I would not exclude the idea that ordinary life is a product of some kind of idea, and that evolution of man is also the product of such a process. The arguments against that idea are not very good, and people admit that they're not too clear about the origin of life. So I think in the end, one will have to, one will get a better account by taking that kind of model than by having Darwinian models or neo-Darwinian ones.
So it's also a guiding process that guides evolution.
Yes, how it would work exactly. It'd be it's the way your mind directs everything you do. It intervenes at various points, even though you've learned something. The mind intervenes. So in a way, this aspect of mind would intervene in evolution to produce the intended result.
But some people would think, oh, this is some supernatural activity. Other people would think, oh, maybe it's some extraterrestrial activity. I mean, so you think it's some sort of intelligent thing embedded within physics, right? Or you think it's some...
I mean, it depends where physics is, and those are just words, natural and supernatural.
And this topic is highly politicized, right?
Yeah, indeed. Especially in as regards teaching in schools in the States.
So I'm just gonna say thank you very much, Professor, for your time, and I hope we can do this in person one day.
Yeah, okay. So, well, thank you.